Trees growing in nature typically develop root flares at the stem-root junction. Root flares develop because roots that are major suppliers of water and nutrients to the leaves are the recipients of the bulk of sugars translocated back down to the root system. It is the supply of sugars from the leaves that stimulate additional cell division in these areas, which create the root flare. As roots extend out from the root-stem junction, additional branching occurs. Several feet out from the stem of the tree, most roots are in the upper 10 to 12 inches in heavy soils with marginal drainage, and perhaps as deep as 12 to 15 inches in well-drained soils. A few roots do extend deeper, but they function primarily when the upper soils are dry, which allows oxygen to penetrate to their depth. Roots require oxygen to function. Girdling roots are part of the natural phenomena independent of man. In this case, a live oak that was native to a site has two girdling roots that were exposed with erosion. Note that the roots have been exposed long enough that they have begun to develop bark-like patterns. It is important to note that roots crossing stem tissue typically has an undesirable girdling effect because the natural downward flow of sugars is restricted. On the other hand, roots crossing roots simply leads to root grafts with little or no complications. More on this later. Trees grown from bare root liners and harvested balled and burlap typically have few roots in the ball of soil. If any of the fine roots present are disturbed, the tree is subjected to even greater stress. This is why such great efforts are made to keep the huge soil balls secure. This green ash shows the major roots present in a soil ball. There were likely several smaller roots that were broken away as the soil was removed. The dominance of the taproot prevented all but a limited number of more horizontal roots to develop. A major problem with harvesting trees balled and burlap is the fact that 90% or more of the roots are left in the field. In this case, a London plane tree that had been bed grown and undercut twice before planting in the field was harvested crudely with a backhoe. The stem diameter was about 2.5 inches. The ring is 24 inches in diameter, or about the size of the soil ball at harvest. But this shows the extent of the roots left in the field. The other major problem with balled and burlap trees is the fact that first, root buds must be initiated at cut root ends. Only after buds are formed can new roots begin to grow. Development of root buds is very oxygen dependent, whereas new roots that extend from those buds are typical of the species. Lack of oxygen at cut root ends that are installed more than 6 to 10 inches below the surface frequently limits root bud formation. Comparing typical roots included in balled and burlap versus root tapper containers is dramatic. For every root included in a typical B&B root ball, there are hundreds in the root trapper. The tree on the left is a Shumard oak, whereas the tree on the right is an ash. Stem diameters were about the same. The oak is 2 years younger than the ash. In the early days of growing trees and other woody plants in containers, it was thought that once the plant was removed from the container and planted, a root system typical of the species in nature would develop. Clearly, that is not the case. Once the root is deformed for any reason, it will remain in that position for the life of the plant. The two tree seedlings on the right were propagated in typical plastic rose pots. The live oak seedling on the left was propagated in a cylindrical plug with smooth sidewall and one opening at the bottom. This live oak seedling was removed from a 3-gallon container and most of the mix was washed away. The root system was relatively fibrous for a live oak. Some roots had extended out to the sidewall and were circling. The reason for the investigation was that the root completely encircled the stem. Had only the top circling root been cut and the tree planted to grow on, the problem would have remained a secret. When the outer roots of the tree in number 11 were carefully cut away, it was clear that the seedling had been propagated in a cylindrical plug tray. Note the series of circling roots on the seedling. Also note the tip of the knife that marks what had been the bottom air pruning hole of the plug. Nearly all of the fibrous roots seen in number 11 resulted from roots growing up and branching out from the bottom of the plug. Such undesirable production practices still exist today, and unless an autopsy is done, the cause of poor tree performance is not disclosed. Growing tree seedlings in conventional round containers nearly always ends up with grossly deformed and circling roots. In this case, note that the first root circled in a container about 4 inches in diameter. Then the plant was shifted to a 1-gallon container where it circled again, then into a 3-gallon container with further circling. This plant is worthless. In 1983, I prepared a huge block of 4 different species of trees in the field. The tree seedlings had all been grown in the same way, but after 2 growing seasons, some had grown little, while others had grown a great deal. Since no treatments had been imposed on the trees, there was no explanation for the large growth differences. When the trees were dug with a backhoe, the difference in the growth became very clear. All tree seedlings that had developed many branch roots at the root-stem junction were large trees. Tree seedlings that produced a limited number of large roots that extended out and then branched were much smaller. The results were the same for the loblolly pine, Shumard oak, lacebark elm, and silver maple. The data were clear. Stimulate more root branching at the root-stem junction, and trees grow faster and are more securely anchored in the soil. Techniques to consistently accomplish this required many years of additional research. When the tip of an active growing taproot is air pruned 4 inches below the seed, secondary roots promptly develop along the vertical axis. Note the 3rd seed from the left has not reached the bottom, whereas the 4th seedling had reached the bottom, was air pruned, and secondary roots are beginning to develop. 3 days later, the secondary roots were well developed, as shown by the 2 seedlings on the right. By contrast, if the taproot is allowed to extend 8 inches before air pruning occurs, secondary roots still develop back only about 4 inches, leaving few or no roots along the upper 4 inches of the taproot. I call this the 4-inch rule. It appears to apply to all roots. This is the same phenomena that allows frequent top pruning to create a dense hedge. The Rootmaker 2 propagation container is 4 inches deep and guides the tip of the taproot to air pruning at the base. It also includes sloping ledges to intercept secondary roots, guide them to openings and corners for additional air pruning to stimulate tertiary branch roots. The catalpa root system on the right was removed from the unique shaped container. The catalpa root system on the left had most of the propagation mix washed away to better show the fibrous root system. In order to better observe the root branching along the taproot of eucalyptus seedlings, a number of root balls were cut in half until one paralleled the taproot. Note the taproot and position of secondary roots on the seedling on the left. In this case, a white ash seedling was air pruned at a depth of 4 inches and secondary roots promptly developed. A few of the secondary roots were cut away to better expose the taproot and distribution of the secondary roots. Looking down on a maple seedling with the top removed shows the radial distribution of roots around the taproot. This radial distribution of roots continues down the full 4-inch length of the taproot on nearly all species. Roots continually extending outward from the original taproot are highly unlikely to create girdling roots on the main stem at any point in the life of the plant. To determine rate of root extension following transplanting, catalpa seedlings were evaluated after 0, 4, 8, and 12 days. Note the tremendous number of roots produced and their length after only 12 days. The original root ball at the left is 3.25 inches square and 4 inches deep. Note that roots had grown in all directions from directly down to all angles and positions. When stem growth is supported by vast numbers of roots, stem taper and strength is enhanced. By contrast, with conventionally grown or native trees, few distinct root flares developed. The entire base of the tree becomes a root flare and remains more or less uniformly bulbous. The oldest trees grown with this system are 14 years and about 12 inches in diameter at the base. The Shumard oak, London plane, and Callery pear trees were all planted at the proper depth. To date, no distinct root flares are visible, yet the entire base of the tree is a flare and is much larger than the stem 2 or 3 feet above. This London plane tree was one of many that were propagated from seed in root maker containers 4 inches deep, then planted directly into the field. Note the array of roots that developed radially as well as downward. Tree seedlings propagated in root maker containers and then transplanted into a larger root maker container also continue the root pruning process and develop stout stems and fibrous root systems. The root system on the left shows the root system with most mix remaining, while the one on the right had most mix removed. Note that some of the roots are likely to form root grafts in the future, but that is a normal process that causes no complications. Root maker containers stop roots from circling and stimulate root branching on all species. In this case, the 1 gallon root maker container was removed to show the array of white root tips poised to grow in many directions. When transplanting occurs, white root tips extend in the direction they were positioned in the container. Young trees grown in root maker containers and transplanted in a timely manner in the field greatly improve the number and distribution of roots in the field soil balls at harvest. These 2 tree seedlings were propagated in root maker propagation containers. The one on the left was transplanted into a 3 gallon root maker container, whereas the one on the right was transplanted into a smooth conventional container. Note the severe circling roots on the plant on the right versus the many fibrous roots poised to grow in all directions on the plant from the root maker 3 gallon. Trees begun in root maker propagation containers, then grown to a larger size in 1 or 3 gallon root maker containers, are being planted into the field to be harvested B&B. Trees grown in this way are far superior to conventional containers or bare root seedlings planted in the field. Trees in the foreground are Chinese pistache in 65 or 100 gallon white root trapper containers, while those in the distance are Shumard oaks in similar containers or root builder containers. All are excellent specimens with stems 4.5 to 6 inches in diameter. All were grown using the root maker system from seed germination and have masses of fibrous roots. Trees grown in this way are ready to be planted into the landscape at any time, even the hottest day in August. With the broad, flat root ball, these trees do not need to be staked once planted. These trees typically make a similar flush of growth the spring following planting in the landscape as they did the spring before while still in the container. When a root system of a Chinese pistache from number 25 was partially washed free of mix, thousands of roots were exposed. Roots extend outward from the base of the stem in a 12-inch deep profile. The root trapper or root builder containers prevent root circling while stimulating root branching. When roots are positioned to extend horizontally in a zone from the entire vertical profile, the tree is promptly anchored on the new site following transplanting. In addition, by having roots poised to extend horizontally, drainage and aeration of the landscape site becomes less of a critical factor. Roots are also poised to extend downward if soil conditions and aeration allow. This lacebark elm was grown in a 45-gallon root builder container, then mix was partially washed away to expose the fibrous root system. One would have to work to kill this tree. When trees with root systems like this are planted and given even a minimum amount of water, losses are unlikely and performance is practically guaranteed. Trees grown using the root maker system quickly develop thousands of roots out into the surrounding soil. This green ash had a 4-inch diameter stem at time of planting from a 30-gallon container. This photo was taken 2 months following planting. Note the uniform flare at the base of the stem. The stem appears swollen and has a strong taper from soil line upward. At this point in time, and when inspected again after 5 years and 12 years, no individual root flares were visible. The base of the stem continues to increase in diameter in a nearly circular fashion. This is due to a massive number of roots off the primary taproot supporting growth of the top and receiving sugars in return. This is a distinct contrast to trees in nature or that have been grown conventionally from bare root stock and that typically develop only 5 to 12 root flares. Root grafts are a natural phenomenon. Root grafts occur on most, if not all, species, and to date, no detectable restriction of growth of tops or roots has been documented. Note that where one root has become fused with another, there is no swelling on either root on either side. If flow of water and nutrients up to the leaves was restricted, or if flow of sugars from the leaves back down was restricted, a swelling would occur at the point of blockage. These roots are of a willow oak with a stem diameter of about 10 inches, growing in a heavy clay soil. Extensive research has been done on the phenomena of water and nutrient transfer from roots to leaves and the return of a portion of the sugars manufactured back to the roots. The root on the left was typical of an unrestricted root. The root on the right was girdled in two places at the top of the photo and to the upper right. Note the swelling of the root back from both points of girdling. In this case, the swelling of the roots results where sugars from the leaves were blocked from continuing to the smaller roots beyond. Remember that a root grows in a given direction from point of origin until blocked, deflected, or is in some way altered. It then grows in a new direction, but it may encounter features that alter direction many times. Roots grow where conditions are favorable. When trees are planted too deeply, especially in heavy soils, and the best growing conditions are near the surface, the likelihood of circling roots is increased. When this phenomenon occurs once or more in the nursery and again in the landscape site, circling root complications are more likely. Developing a broad, shallow root system is highly desirable. In nature, this takes many years. We are simply speeding up the process. An old saying regarding field-grown trees harvested balled and burlap planted in the landscape: the first year they sleep, survive but grow very little. The second year they creep, that is, they grow a little bit. The third year they leap. Reasonable growth typical of the species resumes. Trees grown with the root maker system from seed germination to time of planting into the landscape typically make a normal flush of growth the first year following planting in the landscape. Root maker trees consistently leap following planting. Forget about having to explain to your customers about the old sleep and creep adages.